So when we talk about models, we should understand that there are classifications, just as in science maturity, there are classifications of models we suggest in our book. First are primary predicted models, and these can be thought of as in association with class 1 science. And the example that we give here is the one, as I said before, that I talked about in my previous talk, that shaking a baby really, really hard can produce a subdural hematoma. All right, so let me review this case for you just for a moment. In 1968, an investigator named Omaya was funded by the federal government to try to understand whiplash. You know, we were concerned about whiplash in the late 60s. Should we put protection devices on the car seats behind us in case we get hit from behind? Seems like a good idea, but it's also an obscuration, right? You can't see as much. So what's the trade-off? What do we do? So Omaya, who was world expert in, among other things, loss of consciousness and a consultant to the boxing community, of all things, did the experiments, and his animal model was a rhesus macaque. And he accelerated them from the rear and in order to measure and understand the forces required to produce subdural hematoma and other damage in the subjects. I'm not sure you could get through a board these days to do this experiment. But again, in the quick review of the case of shaken baby syndrome, those are very, very good data. And what he found was that you needed 40,000 radians per second squared to create damage in the rhesus macaque model. In his Journal of the American Medical Association article, he extrapolated to the human adult head and neck to determine that we needed 7,000 radians per second squared minimum to create the damage, right? So a few years later, 3 or 4 years later, an investigator named Guthkelch posed a question. I wonder if you shook a baby hard enough if you could create a subdural hematoma. There was no evidence. Simply a paper that was headed in this direction provided this sort of parenthetical. About a year later, another investigator named Caffey answered the question with no evidence whatsoever. Using his credentials as a radiologist, he said, yes, you can. And people do it, and they're doing it all the time. He published another paper within a year that extended his new scientific fact to a family syndrome, and within another 2 years published yet another paper that extended his family syndrome to a world pandemic. And he linked everything from mental retardation, not just subdural hematoma or neck damage, but everything mentally bad to the shaken baby syndrome. Now, a parenthetical on the parenthetical that helps us laugh about ourselves. Within medical science, do you know that the words imbecile, moron, and idiot were scientific terms, right? And that worked in terms of your IQ until at some point someone said, we can't be calling people morons. You know, we need a new scientific medical literature taxonomy here. So it got changed from those to severely, profoundly, and moderately retarded. And that worked for a while until it was, we can't be calling people retarded. And so now we have, what, educable, trainable, and I forgot now, categories. So anyway, in the shaken baby case, now the scientists got involved. And they said, all right, we now have the phenomenology measured by Omaya, the extrapolation to a human adult, and because force equals mass times acceleration, we have to interpolate for a baby. What would be the force necessary? Well, the interpolation was 11,000 radians per second squared. The scientists now had their hypothesis. And off to the laboratory, certainly we're not going to shake babies, right? We're going to shake models, high-fidelity Department of Transportation models. And what was found was that Purdue linebackers, no less, Purdue linebackers, could produce 1,100 radians per second squared. The threshold is 11,000 radians per second squared. So the conclusion was a human can't actually generate that much force. That study was replicated and confirmed, 1,100 radians per second squared. A separate study was done by a faculty at USIS who said, are you people all crazy? If you got anywhere near 11,000 with an infant, the neck would disrupt, essentially would decapitate. Right? So the science community felt like it has done its job, but that didn't stop medicine. And now we still have cases of shaken baby syndrome. Today's talk is not about that, so I will get back off this path and back to where the shaken baby syndrome evaluated as a scientist and not as a medical practitioner would be in our category here. It is, it was a false predictive model. On primary models, we place secondary and tertiary models, and in sequence, as you go from primary to secondary to tertiary models, they are depending on the lesser. So secondary depend on primary models and so forth. Actually, let me go back for a moment. On the primary predictive models, I mentioned a few minutes ago that we must be wary, must be very cautious about what we call the lure of mechanism. For the very reason that I just mentioned, that we're not going to go shake babies, obviously we're not going to do that. What we do then in science is called reduction. We take the phenomenology down to a reduction and we look at mechanisms of injury. In the case of the shaken baby syndrome, you have elaborate descriptions of the crossing veins, the disruption of the tissue in the dura and below, the vascularization of the dura and below, and you have these elaborate descriptions. Well, that presents a lure, and we call it the lure of mechanism. It sounds so attractive physiologically and medically that I'm not really worried about questioning the basic phenomenology itself. I'm there. You know, I can now explain what's happening at the reduction level. Okay, the best available information covers all processes that attempt to describe technical information applicable to need. And the example that we give here is testing for efficacy and safety during the production process for a new product. Example, FDA, it's testing of new drugs. And by the way, we think there's going to be a major change in the way FDA controls the testing of drugs. Today, I believe it's about 14 years to go from idea to market. A very small percentage, something like that, small percentage actually makes it to market, and the R&D costs are very high, and our strict rigidity and understandably so on safety is going to prevail. But there may be ways to parallelize the production through the R&D process using in silico modeling and simulation and so forth, and that's very, very encouraging. But the FDA, the EPA, other regulatory bodies use the science that's produced by engineers, scientists, to make decisions. And I'll repeat yet again, our point here is that they need to understand the maturity of a scientific trajectory when they make a decision about our lives. So this is all about ethics. And if we talk for a moment about the ethical use of science as scientists and consumers of science, it is extremely important to understand that the responsibility of the scientific community and individual scientists to make sure that society as a whole is provided with relevant BAS information, which is a repeat of what I just said. An example that we give here is, quote, all research organizations are required, important word, to establish an institutional review board, an IRB, to review experiments including human subjects. Well, that we use the word required means it's not an ethical issue, it's a legal issue. It is legally required that we do this before we use human subjects. And, and that institutional review board needs to understand the reliability, level of maturity, that is BAS, and recognition that there are areas outside their purview of science that need to be taken into consideration.
Excuse me,
yes, sir.
BAS means?
Best available science.